Suggestions for mod 4. 64. Other suggestions? 73. That's a good one. Okay. Any other suggestions?
80.
Last chance. Get your nomination in. What?
78.
78? Was there another one?
69.
Okay, I think that's plenty. So vote for 0, 1, or 2 of these. 64, 69, 73, 78, or 80. Take a look at those. You can vote for 0, 1, or 2. All in favor of 64? All in favor of 64? Is it 64? 69? 73? 78? 80? All right, so it's between 69 and 78. So for 73 for sure? Between 69 and 78. All in favor of 69. All in favor of 78. 78. Okay, those two. 73 and 78. Okay, and you're folding it up and handing it in. So, since we look and we see that they're going to say they want the number of years since 1970, well, that's the number of years since 1970 is going to be our input. So at 1970 that'll be 0, and at 2000 that will be 30. So what is our population in year 1970? 3562. Right? And then in the year 2000, 30 years later. So if this is exponential growth, immediately something should pop out at you and say, oh, I can get the very key, what is it? Yeah, so if you've got a population and a population 30 years later, then that should immediately make you think, okay, if I want to model this exponentially, I can immediately get that growth factor. And growth factors are, in general, what are they? Multipliers on output or input? Output. So it's going to be the multiplier on 3562 that results in 9765. We're asking what number would you multiply by that 3562 by to get 9765? How would you find it? The ratio, right? So 9765. That ratio would be what you would need to multiply this population by to get that population. I get 2.741. So to get the population that for part A, the population that models the population since 1970, I'm going to have, call it F. T years since 1970. Well, I'm going to have the population, the initial population. And then I'm going to have 2.741 to the T. Is that right? What is the 2.741? 30-year growth factor. We want T to be the number of... So, as the way it stands now, what would T represent? The way this stands now? That'd be periods. How many 30-year periods? If we plug T equals 1 in there, that would signify jumping ahead 30 years because we'd multiply by this 30-year growth factor. And if we put T equals 2 in there, you'd be multiplying by this twice, and you'd be skipping ahead 60 years, right? So we want, if that's going to be our 1 year, then what needs to be inside there? We need, if these match, right? So whatever growth factor this is the 1 unit growth factor for whatever that exponent is. So if we want this to be years, then inside we need the 1 year growth factor instead of the 30-year. So there's some number, call it B, that's our multiplier for 1 year at a time. How many times would we have to multiply that B together to have the same effect as multiplying by 2.741? Yeah, so if each B is the multiplier for 1 year, and we multiply that B together 30 times, it would have the same, should have the same multiplying effect as the 30-year growth factor, meaning that B would be 2.741 to the 1/30th. So that's what I want here. So now I've got my 1 year growth factor in there, which corresponds to my 1 year unit. T is 1 year. So let's get that as an approximation. So 3562. What is that approximation? 1.0, if I remember correctly.
1.034.
Is it 342, I think?
Yeah.
Yeah. So if we simplify that 2.741 to the 1/30th, we get this. What's the percent increase per year? What's the percent increase per year? 3.42%. Is that a continuous rate or the true percent increase? True, because it's based on the true growth factor, right? So we talked about the annual percent change. We just said that. And that's the true percent increase of 3.42%. Okay, predicting the town's population in 2019 means that T is equal to, I believe, 49. Is that right? 49 years after 1970. So we would start with the initial population. And how many times would we multiply by the 1 year growth factor? 49 times. That's why the function works, because if you put 49 here, it has the effect of taking the initial population, multiplying it by the 1 year growth factor 49 times. And will give us the population 49 years later. So that's just f of 49. When will it reach 40,000 people? So now here's got my function. What does 40,000 have to do with this function? Someone suggested that'd be the output of the function. Agree? Yeah, so we want to know the number of years, the input, to reach an output of 40,000. Okay, first step. We're going to divide, right? So we're going to do 40,000 over 3562. 11.23. So that ratio is 11.23 is equal to 1.0342 to the t. So now we're ready to find out what t is. T is what kind of thing?
Exponent.
An exponent. And we know we can rewrite exponents as? Log. What exponent is it? It's the, you read it right to left. T is the exponent of 1.0342. That gives 11.23. Just read it left to right. T is the exponent of 1.0342. That gives 11.23. Okay, so all we need to have left is change a base. So you want to use a base that your calculator can do. That's either base 10 or base E. Take your pick. Base 10 would just be log of over log of the original base. So log of 11.23 divided by log of 1.0. I get 71.9 for t. What does that, someone else get that? What does that mean? He said the number of years until the population reaches 40,000. That's right, that's our t value that would give us an output or a population of 40,000. And so that's, I think, what is that? The year 20, in the year 2041? Near the end of the year 2041, we'd hit 40,000. If this growth pattern continued exactly the same way. Okay, so if we followed this pattern of growth exactly the same way, then it'd be 2041, we'd hit 40,000. All right, I'll just stop. So it's lots of principles here from all of Module 4 coming into play. Questions? Yes, sir?
For C, for calculating the population in 2019,
Uh-huh.
we've done the population 2000,
And made t,
19.
yep, if it's 2019, yeah. So you could put that 9765 in there, and then advance only 19 years ahead. Yep, should get the same thing. Absolutely. Other questions? Okay, then I think it's asking for how long it will take a population to triple. Is that right? Over here. Okay, so we want the population to triple. So basically we're saying if we start with any, kind of the way he was thinking, if we start with any population, call it P. Then how are we going to get the population t years later? We're going to multiply it by 1.0342. How many times? T times. So we're interested in that population becoming 3 times what you had before. So you could use A here if you want 3,562, that's fine, and then you'll take 3 times that. But it doesn't have to be. It can be any population starting at any time, as long as the growth maintains the consistent growth factor. Then we want to know how long, how many years to reach 3 times whatever you started with. So dividing both sides by p, we get 3 equals 1.0342 to the t. T is the exponent of, that would give 3. T is the exponent of 1.342, that would give 3. Change of base, let's use ln this time. ln of 3 over ln of 1.0342. Anybody got that? ln of 3 divided by 32.7 or 67 years. Is that right? Same process as before, but now we're just tripling whatever population we start with. After 2 years, we want to have 3 times that amount. Questions on 73? Those who asked for this, does it help? Any further questions? What was the next one we said? 78? Okay, so it says the population increased 2.1% per year. Is that referring to a continuous rate or actual percent increase? If it says the population increased by 2.1% per year, that's actual increase, and from that we can get yeah, but before that, if we want to model the growth. Will that give us the 7-year growth factor? Yeah, so if this per year per percent increase, then that's the 1-year growth factor. T years since 2003. So if it's going to be T years since 2003, we want the initial population in 2003, 292,430. So we're going to do e to the kt. So we're going to, for this, is this going to use the exponential continuous form? No, it's going to use the a. This is b, right? This is our true growth factor for 1 year. So we're going to use the a, the old original form that we had. A, b to the t. Okay, now they want us to rewrite it in the equivalent continuous form, which is a e to the kt. So in order to really, the only thing we have to figure out to write that is what? We got 4 variables there. We got a, e, k, and t. The only thing we really need to figure out to write it this way is k is the only thing, because we already know a. A is same, starting value. So e to the what? And t is our input, so it's going to stay t, right? That's the input. So the question is, what goes here? So e to the k is the same as b, right? So e to the k is b, and we know what b is, 1.021. So look, we need to know what an exponent is. What exponent is that? That's the exponent of e. That would give 1.021, which is so all natural logs in general. All natural logs are what? What are they in general? They're always exponents of e, right? They're exponents of e that would give you whatever you're taking the natural log of. These are always exponents of e. Tell me again what it was? 278? Oh. Zero, I see. Sorry. Okay.
Could you just look at what they gave you, the 2.1%?
Uh-huh. You want to put 0.021 in here? Is that what you're saying? Yeah, no, so the whole thing is B equals e to the k.
No,
The
but,
true percent is different than the continuous rate. The
Right.
true percent is 2.1%, different than the continuous rate.
but if you just move it over 2 times, then it's then it's just the decimal form of that, and that's k, right?
Do you want to move the decimal over here and that's k?
It's 0.021.
No, that's the true percent increase. K is a different, see, it's a different number. It's close to it, but it's different. And that's because it's the continuous rate. So no, they're different. They're not the same number. It's just they're really close because this percent is so small. When the percent gets bigger, the difference between these becomes more drastic. 0.02, I'm just going to go with 208, round it up to 208. So what's the continuous rate? The continuous rate is 2.078% versus 2.1%. Those are slightly different values. Which one is the true percent increase? First one or the second one?
First.
It's the true percent increase. The second one, that's what we're given, right? That's the true percent increase. It gives us the true growth factor. This is the continuous rate. Both of them model, even though they're different values, they model the exact same growth. How is it possible? How is it that these two, this continuous rate and this true percent increase, reveal the exact same growth? We've said it 50 times. Can anyone say it? Yeah? Which one am I going to combine with compound? Right. When I combine it with moment by moment compounding, the effect in the end is to actually grow the quantity this much per unit instead of that much per unit. So this is what you have to do along with, so you have to take this and add to it, not add to it, but include with it continuous compounding. And what your result is that true percent increase. That's what a continuous rate is.
So if you graph these, would they be different functions?
These two right here,
Yeah.
exactly the same. That's what we're saying. Exactly the same growth.
So on the graph, they'd be the same one.
Exactly the same. Why? Because we forced that e to that to be the same as that. They're equal. So that thing in parentheses is the same as that in parentheses. That's where we got this number in order to make what's inside the parentheses the same. Same graph. Same growth, same graph. Does that answer all the questions on this one? Yeah. Any more questions on Module 4? We don't really have time. There wasn't enough votes for it. So after class, I'm happy to talk about it after class if you want. Okay. Going. Okay, so I'm going to definitely talk about number 7, the skateboarder. So of 1, 2, and 3 in Module 5. Suggestions for that? So number 1 was the fishbowl. Number 2 was working backwards from the graphs to build the bottle. Is there one of those two we should do?
2A. I had a hard time.
2?
Two.
All right, let's do 2. So if we do 3 and 4, would that be good?
Yeah.
Let's do 3 and 4. Okay, so let's remind ourselves of the approach to these covariation problems. I'll write it down here. So the first thing is we look at small equal increments of input or output? Input. Okay, small equal increments of input. And the first thing we look at for each increment, we look at we ask about the output. What does the output do? Does it go up? Does it go down? Does it stay the same? And that creates a change, right? That creates a change in the output, whether it goes up or down. So we look at that first change. Then we want to compare successive changes in output. Meaning, how does the current change in output compare to the previous change in output? This is the most important thing. Because if you can get this, then the last thing is easy. So we compare successive changes in output. And then the third thing is we conclude about the rate of change. Ask about the rate of change. What's the rate of change doing? Is it increasing, decreasing, staying the same? Okay. So first thing we're going to do here is we got this bottle and we're going to look at equal increments of height or equal increments of volume. Volume, right? We're going to start and look at, so I'll just split these boxes in two, okay? And that'll be our equal increment of volume. The way that those grids are, I'll just go in two. So we look at the first amount of volume added and we say, what happens to the height when I add that much volume? It increases. How much? This much right here, you see that? That's how much it goes up. I'm going to add a little bit amount of water. Oh no. Okay, so I'm going to add another little amount of water. How much will the height, so what will happen to the height? Up or down? It's going to go up. And then how does that, so question 2, how does the new change in height compare to the previous change in height? It's the same. I'm going to try to make this even bigger. Okay, so hopefully that'll help a little bit. So we got that first change in height. It's right here. And then we add the next amount of water and we do the next change in height, and we said that that change in height is how compared to the previous? The same. Next change, next amount of water. The height's going to go up. That's question 1. Question 2, how does that change in height compare to the previous change? What do you think? How does that one compare to the previous? They're all the same because this graph is? Yeah, it's linear. So for equal changes of volume, we end up with equal changes in height, right? For equal changes in volume, we get equal changes of height. What kind of rate of change is that? So in this first part of the bottle, call it part A of the bottle, we have constant rate of change. Ignore this. Because equal changes in volume are giving us equal changes in height. Or like when we talked about constant rate of change is additive. For every time you add the same amount of volume, you're going to add the same amount of height. Additive growth. All right, so now here we are in section B of the bottle, from here to here. I'm going to do my same change in volume. And what will happen to the height? Increase. More or less than the previous change? A lot more. In fact, suddenly, so this point right here, that corner, means that suddenly we're going to get a large change in height for the same change in volume. So an abrupt change in height. Okay, and then next amount of water, what will happen to the height? Increase. This increase, or this change in height, how does it compare to the previous change? It's less. Do it again. Add some water. What happens to the height? It goes up. The height goes up. What about the change in height compared to the previous change? So changes in height are doing what? Changes in height, this is the key. Changes in height, or changes in the output, are decreasing or increasing? Decreasing. What's the height doing?
It's increasing.
The height is increasing. We're adding water to the bottle, so the height's increasing. But the changes in height are decreasing. See, each change is less than the one before. So what about the rate of change? Is it constant? No. Constant rate of change means equal volumes of water result in equal changes in height. We don't have equal changes in height. We have decreasing changes in height, which means the rate of change is increasing or decreasing? Yeah, if the changes are decreasing, then the rate has to be decreasing. Should make sense. And what if the rate of change is decreasing, then what happens? Those changes are getting smaller, and so the graph doesn't stay in a straight line constantly. It bends down, right? So that's called concave down. Cupped, it's cupped down. You can think it's cupped down, right? Concave down. And that happens when the changes in height are decreasing, and then therefore the rate of change is decreasing. Okay, last part of the bottle, part C. I add the next amount of water. The height goes up. Add the next equal amount of water. How does the next change in height compare to the previous change? Okay, so the height is increasing, and the change did what? Increased or decreased? Increased. One more time. So suppose this goes up like this, that, okay? So same volume of water, height goes up. What about the change in height? These changes are increasing. So the rate of change is increasing. The rate of change is increasing because the individual little changes are increasing. And so if the individual changes are increasing, those steps, the height of each step is more than the one before, what's going to happen to the graph? It's going to curve up. It's going to curve up. It won't be constantly increasing with equal changes, but the changes are getting greater, so that makes the curve will bend upward. And so this is called concave up, like a cup. All right, the changes in height are increasing. When changes are increasing, it's curved upward. Okay, so drawing the bottle. So if it's a constant rate of change for equal volumes of water, we get equal changes in height. What will that bottle look like? Yeah, it'll be like just with straight sides. And then we said there's an abrupt change. All of a sudden, we get a much greater change in height. So it's going to get narrower. Gradually? No, all of a sudden, abruptly, it's going to be narrower all of a sudden, like this. It's going to be suddenly narrower. And then our rate of change decreases. So if the rate of change is decreasing for equal volumes of water, what will the bottle look like? The height is going up, but going up at a slower and slower rate. So it's going to get wider. all the way up to here. It's getting wider. And then if the rate of change changes and starts to increase again, that means that it must be getting narrower because the same change in volume is causing greater and greater changes in height. So here's this very common looking bottle here. Everyone's got one, right? Something like a lava lamp, but the whole thing, even the base, right, is all empty until you fill it up. Okay, does it make sense? Any questions? So what will this look like? So we've got a linear graph, means that changes in height give equal changes in, equal changes in volume give equal changes in height, but very small changes in height. So what would the bottle be like there? Really wide, right? Really wide. And then suddenly it will get a little narrower, but then from here to here, what will the bottle be like? Won't it be straight sides? And then suddenly, narrower again. And so for equal changes of volume, the height changes, changes in height are equal, but they're much greater. And then here it's going to get wider, and then back to a very wide at the end. So that's something like what this will look like. So that's that bottle, something like that. So there's no concavity here because every rate is a constant rate. You got in each part of the bottle for equal amounts of volume, you get equal changes in height until there's abrupt change, until the next one. Okay, questions on this so we can get to the skateboard. Got to work on the skateboarder here. Are we good? Okay, so the skateboarder, what is the input quantity for the skateboard problem? Time. Time since leaving the starting position, which we know is up in the upper left, right? Here's the key to this one. What is the y, or the output quantity for this covariation? Here's the key. Horizontal distance from start. That's what makes this a good question. You really have to think about it, and it forces you to use this method that I was talking about. We're going to look at equal increments of what? Time or distance? We're going to look at equal increments of time, and that's why I've got the grid here. And for each increment of time, we're going to ask, what does the horizontal distance do? What are the changes in horizontal distance doing? And what is the rate of change doing? Those are our three questions. What is the distance doing, horizontal distance? What are the successive changes in horizontal distance? How are those changing? And then how is the rate of change changing? So I'll just draw it real fast here. So it's almost vertical, and then flat at the bottom, and then like that. Not bad. Okay, so he's going to start here. Start. And we're measuring horizontal distance from the start. Okay, we're measuring horizontal distance from the start. So first little amount of time. What happens to his horizontal distance? Increases or decreases? Increases. A lot or a little? A tiny little bit, because his motion is mostly vertical. So he does go out to the right a little bit, but not much. So do that right there. Just a little bit. Next increment of time. His horizontal distance does what? Increases. A lot or a little? More or less than before? A little more, because now the ramp is starting to bend horizontally. So with the next amount of time, there's going to be a little bit more of a change. Which you can see if I get rid of that. There we go. Now you can see it. So, all right, next increment of time. Getting close to the bottom of the ramp now. What will happen to his horizontal distance from start? Increase. The amount of increase, more or less than the previous? More. So we're getting points here, right? We're getting points on our graph. One more time. He's almost to the bottom. Next increment of time. What will the horizontal distance do? Increase. The change, greater or less? Maybe one more time greater. Now he's going across the bottom. Next unit of time. The increase in horizontal distance will be greater or less than the previous? Yeah, going across the bottom, it's virtually a constant rate, so it's going to be the same. So these two are the same. So in the first part, the changes are, as he's heading down the ramp, the changes in horizontal distance are doing what? Increasing, which means that the rate of change is increasing, and the graph is? No, the graph is concave up. Concave up. That's what the change is increasing means. The graph is concave up. Okay, then across the bottom of the ramp, changes are doing what? Staying the same. So the graph is straight line. That's an attempted straight line, not bad. So concave up as he comes down the left side. Then as he goes across the bottom, equal changes of distance for equal changes in time. And then as he starts heading up the back side, increment of time, how will the increase in distance compare to the previous? A little bit less, and then a little bit less, and then a little bit less, until he's at point B. Okay? So for this part, the changes are doing what? What are the changes in his horizontal distance doing? First of all, what is his horizontal distance doing? Is it increasing or decreasing? It's increasing. The changes in horizontal distance. Decreasing. So the rate of change? Decreasing, and therefore the graph? Concave down. Oh, it's doing so good. Okay, concave down. Something like that. Okay, so here, this on the way back, it starts to get confusing, okay? So you might think, oh, it's just going to be the reverse and we just keep drawing it. Well, maybe so, but there's a really important thing here, and so I know we just got 5 minutes left, but try to stay tuned. So we're going to go, here he is at point B, and he's at his pause point, so here's point B. Next unit of time, what will happen to the horizontal distance from start? Increase or decrease? This is the stop. B is the stop point. So now, after the momentary pause, we're doing the next increment of time. Will his horizontal distance increase or decrease? Decrease. A lot or a little? A tiny bit. Okay? What kind of change is that? Positive or negative change? Is that if it's a decrease, then that change is negative. Okay? So this is a negative, so we'll call it, say, delta D for distance. So delta D is less than 0, negative. Okay, don't tune out now. This is where it gets confusing. Next unit of time. Does his horizontal distance from start increase or decrease? It decreases. He's getting closer. So D1 less than 0. So D2. So D2, is that a positive or negative change? Negative change. So here's the way we want to say it. Is it a bigger negative change or a smaller negative change? It's a bigger negative change. So if it's a bigger negative change, what are the changes doing? Increasing or decreasing? If it's a larger negative change. Okay, the magnitude of the changes are increasing. But if the changes are negative and we get a bigger negative value, it's decreasing. Okay? This is very confusing and it takes a long time to get it. So see how well we can do the first time. So this is more of a negative change. And when values get more negative, they are getting smaller. So the next increment of time, the horizontal distance decreases. Is the change more negative or less negative than this one? More negative. So the changes are becoming more negative. And values that become more negative, are those increasing values or decreasing values? They're decreasing. So the rate of change here is decreasing. What's the shape of the graph? So here's why we do this, so we can have consistency with the shape of the graph. What's the shape of the graph? Concave. Still concave down. So this, we knew this was decreasing rate of change. Here, it's still decreasing because the changes are becoming more negative. And therefore, whenever the rate of change is decreasing, the shape of the graph is? The shape is concave down. So when changes become more negative or larger negative, those changes are decreasing. It's very confusing, but we need it for consistency of concavity. This is decreasing rate of change, slowing down, going in the positive direction, and speeding up, going in the negative direction is still decreasing rate of change because it's concave down. Okay? What happens on the way back? Equal changes in distance, equal changes in time make? Yeah, so now we have a couple units of time there where we have constant rate of change. Equal changes in time mean equal decreases in distance. It's constant rate. And then what happens? The next unit of time, how does the change compare to this one? Less or more negative? Less negative. As he's coming up the left side, each change is less negative, less negative. Increasing or decreasing rate of change? So changes are becoming less negative. Changes less negative, which means increasing rate of change. And the shape of the graph? Concave up. This is very confusing for students, and it takes for lots of students, we have to go over this over and over and over to get it. Because it feels like these changes are getting bigger, right? But they're getting more negative, so they're getting smaller. And these changes, it feels like they're getting smaller. But they're getting less negative, so they're actually getting larger. And we get increasing rate of change or concave up. Okay, so we've got a test the Thursday after break. So because of that, we need to have class Friday to make sure we cover everything. I'm going to post exam studying materials tomorrow, so you'll have 2 weeks to get ready for the exam, and I'll see you Friday.
increasing.